Hello and welcome to this module on memory management now. We have been working on operating systems, CPU, scheduling, and we get now to memory. Why is memory important? Well, you can have all the CPU you want, but if your CPU is not able to run your program on physical memory, which is it is not able to get the data from physical memory and has to go back to the disk, it's really going to run very slow. So memory is an important element of how a program can even run, and if it does run, that it runs efficiently. We will be looking at memory management from the perspective first starting with the hardware on how CPU memory management runs. Then we go to the operating system level with how the process memory management is done, and then getting into how we do new memory allocation concepts. After that, we look deeper into the kernel to see how the kernel actually behind the scenes is optimizing memory for you. So as we get into memory, let us look at memory and addressing as a problem. So we are doing 64-bit architecture here. What does it mean to be at 64-bit when it comes to memory addressing? Well, we can start with 32-bit architectures, and 32 bits, and based on what we learned about bits, we are able to use 32 bits to get to up to 4 gigabytes of memory addressing. Each address is able to address 1 byte at a time, and when you have 32 bits, you go 2 to the power of 32, which gives you the ability to address 4 gigabytes of data. As we expand the number of bits, you go to 40 bits, you are now able to go to 2 to the power of 40, which is 1 terabyte of data. 48 bits, you get to 256 terabytes, and at 64 bits, which is available in a 64-bit system, you are able to address 18.4 exabytes of data. So that is a lot of data. So we have 64-bit systems, but because the need to address that much memory isn't there, the Linux systems that are running 64-bit actually are doing using 48 bits for memory addressing only. Now, let's look at the core problem that you have if you really have a lot of memory, assuming you got that memory. There are some basics about memory management. What if every process were to use memory directly? So let us look at a simple scenario. Say your RAM that you have has 12 slots, and you can say each slot is 1 byte, or you can say each slot is 1 kilobyte. It doesn't really matter. Just assume you have 12 slots of RAM to give away at time 0. Now, say at time 1, you get process 1 that starts up and uses up slots 10 to 12. And you're just assuming you're trying to load the system bottoms up here, 10 to 12, and then go to 1. And then you say at time 2, process 2 and 3 come up, and now you're able to assign process 2 1 slot, which it asked for, slot number 9, and process 3 asked for 2 slots, so you got slot number 7 and 8 given away. So at time 4, process 1, process 2, process 1, and process 3 come up with more requests in that order. So you give 1 slot to process 1, process 2 needed 3 slots, gets 3 to 5, then process 1, another one with 1 slot, and process 3 with 1 slot. So at time 4, pretty much you are used up. Luckily at time 5, process 2 is done and exits. So process 2 opens up its slots, which are 3, 4, 5, and 9. The question now becomes, how do you expand memory for some allocations? Like process 3 is at slot 1, and if it wants to expand that particular memory allocated to it address, how do you do that? Well, you're pretty much stuck, because after process 3, process 1 has taken slot number 2. How do you allocate 4 slots at this point? So you have 4 open slots, but how can you allocate that? Because 3, 4, 5 are open, which is great. You got 3 slots that are directly addressable open, but slot number 9 is far away now. You can't linearly address and provide someone 4 slots of memory. The other problem that comes in when all these processes are running and you still have process 1 and 3 running, how can you ensure that process 1 will not access process 3's memory, and process 3 does not access process 1's memory. In this model, the memory allocations are predictable, so the processes may be, because they want to, bad program, rogue intent, or maybe just bad programming. You can cause problems. So it can be just you have reliability issues, or you could cause security issues with this. So how do you solve for this problem? And the problem has been solved through the use of linear addressing for each process, and giving each process the ability to actually use the same addressing space, but don't give the processes the direct address to the physical memory. So come in between and provide a mapping between the process, what the process is trying to use, and what the actual physical memory is. Because if you do that, you have now the ability to control when there is fragmentation happening on the memory, to move things around and open up physical frames. If you do mapping of linear addresses, maybe you don't even need to do that. You just give them different mappings for different addresses. The process will think it is still working on a linear address space, while the physical address space can actually be distributed. So the CPU solves this problem with using a memory management unit, and the purpose of the memory management unit is to solve the problem of the program code is going to use linear addressing, and the memory management unit will translate that to the actual physical address of the code. So that processes now, they all run their own linear addresses, and they don't care about where exactly in the RAM they're located. In this model, the memory management unit does address level translation, but it also manages a few additional flags for each location. Like, is the memory present? Is it even mapped? Is it readable? Is it writable? Both. Can a user process use it, or is it only available to a supervisor process, which would be like a kernel privileged mode? And the ability to actually flag when this memory has been used, or when the memory has been written to and is dirty now. So this is all great. The problem here is that if you were to consider every piece of memory is virtually available, then you almost need to double your memory. Every address has to have another address where the mapping stays. So that becomes a complicated problem because of the amount of space you will need, as well as because it can be a performance issue. So the solution is that you don't really map every byte of address that you need to access. What you do is you map pages of memory, which is a bunch of memory together, and not every byte. This is why paging comes in, because you're giving a page of memory. So it's called paging mode. It's a page. The size of the page can be different, but it is a page nevertheless. When we discuss paging, then on the physical side, pages are called page frames. So on the right side in the RAM, you will call that a page frame. The default size of a page frame can be different on different architectures. 4K is the default size used in the x86 64-bit architectures, and has been used like that for a long time now. But it's not set in stone. Different architectures can use different ones, but we will, for purposes of working through these examples and knowing that most of the default systems are running at that x86 based architectures, at least, we will assume it's 4 kilobyte one page frame size. So the page frame is 4 kilobyte, and the same name on the linear space is known as a page. And a page is on the linear side, the virtual address, and the page frame is the physical address. So the memory management unit, instead of mapping every address, will now map pages. How do you get now a page? Well, if you use 4 kilobytes and 4 KB has to be used for internal offset of a page frame, that means that the lowest 12 bits, they are now going to be used as an offset. And they don't matter as far as memory mapping is concerned. They're the same whether in the virtual space or in the physical space. Only the bits higher than the 12 bits matter as far as mapping is concerned. So this is how it'll do. The memory management unit will actually do the translation of linear pages to page frames, along with flags that tell you how you can use those pages. So as we get into these, let's run some numbers and use an example to see what will it really mean. So we take the example of 48-bit addressing because 48-bit addressing is actually pretty prevalent in 64-bit architectures. So when you do 48-bit addressing, you have 48 bits that are available to you for address. The total addressable memory of 48-bit addressing is 2 to the power of 48, which is 256 terabytes. And we say that we're using 4 kilobyte frames, so we will use the first 12 bits, the lowest 12 bits, 0 to 11, for purposes of the offset in the page frame. So those are used for the page frame. The rest of the bits, which is bit 12 through 47, that is 36 bits, are available to be defined as the pages. So these 36 bits will have the page numbers. Now, the top 36 bits will be able to provide you 2 to the power of 36 addressable pages, which is 64 gig pages. Now we can take an example here and see, in this particular example, we show a 48-bit linear address, and then we say the top 36 bits are the page number here. So we strip those 36 bits out. That is the page number. That's all that matters to the page number. And the bottom 12 bits, which is in hex 4C2 here, they are the offset. And they will just be applied to the page frame and the page equally. So in this case, you will be able to map using these page frames, and you will have 64 gig pages to manage. Now, if each mapping takes 8 bytes, and if you are going to do this for each process, that's just like a ton of memory. So the solution is actually to not just think of this whole thing as a linear model. In the translation unit, you use different data structures to represent this information. So on the right side, the prevalent paging structures, and at least used in the x86 system, will be the hierarchical paging structures. And we will go to those hierarchical paging structures, what they look like, in just a moment. But it's not a simple table, it's a paging structure hierarchy. So you are able to get to the mapping of the linear page to the page frame. On the CPU side, additionally, for performance reasons, there is another cache for this mapping, because the code will probably be looking at addresses once it is getting and be going for similar addresses that are close in proximity to the addresses they are already looking at. The cache provides a locality benefit. So the cache on the CPU side in the memory management unit is called the translation Lookaside buffer, the TLB cache. And this will cache the same information that you would get if you were to scan and go through the paging model that you have on the right side. So if the entry is present in the TLB, you don't have to go to the paging tables for the mapping. You can just grab it from here. When it is not in the TLB cache, you will, of course, have to look into the paging structures. So this provides a good performance improvement in lookups of page mappings. The next thing we will look at is the hierarchical paging structure. How do you build one? And this is in the x86 Intel architecture. So you basically, instead of saying I have one large page table, you divide the page tables into smaller segmented hierarchies, directories that you traverse to get to the final endpoint. And the way it saves memory is because now if a process really needed a small amount of memory, and it doesn't really need all of them, this provides a much better structure to only physicalize the mappings that you need and keep it close to that level instead of just wasting all the blanks that are in your linear address space. So there are directories here, and each directory has a different name given to it, but they have a similar purpose if you look at this model. On the rightmost side here is the page frame. The page frame is what we're trying to get to. the page frame is that 4 kilobyte structure that has the actual user data. In between, we put a 4-page directory traversal, and each one of these is constructed such that each one is 4 kilobytes per record that will be created. And each of these records will have 512 entries. So they have been structured like that. And the address that you have in the linear address space for 48 bits, we know that the 12 rightmost bits were out for the 4K page size. You were left with 36 bits. And then what you do with the 36 bits is divide those 36 by 4 into 4 offsets of 9 bits each. So these 9 bits become offsets into directory structures. And these directory structures you can traverse then to get to the final page frame. So let us look at the example here. When you start a lookup, you need to know the first place where you will look up an address. So you will go to the first one, which is the page map level 4 table, and you will have the address for the page map level 4 table in your CR3 register already stored. So you know where to go, and then this table will have 512 entries because the table is 4K in size. And you have used the linear address of 9 bits to be able to address 4K, and internally 9 bits can address 512 entries. So 512 times 8 bytes for each entry is 4K. So it's all perfectly matched up for that. So you will go to the PML4T table. You will use the 9 highest 47 to 39 bits and say, okay, where in this table is my offset? You go to that offset, and then you will be able to see over there, mapping to that offset, the physical address space for the next lookup. The next lookup will be to the page directory pointer table. So you go from here, you get to your offset, you go to the page directory pointer table. Now within the page directory pointer table, that's another 4K record. And the offset within that 4K record will be determined by bits 38 to 30 in the linear address. So you use those 9 bits, and you can find another offset between 0 and 511 using the data in that. And that record within the page directory pointer table will point you to the next physical frame, which is for the page directory table. This way you will go to the page directory table. Same thing, you use the bits 29 to 21 to find the offset there to the page table. Then you go to the page table, and in the page table, the bits 20 to 12 from the linear address will provide you the offset to the entry that finally points to the page frame. This is the address in the last page table that you will give back. That is the physical address where the page frame is. That is the physical address where the data is. And the bits 0 to 11 are really the offset within the same page frame. So this is efficient because if you really need a small amount of space, all you needed was one 4K table in each of these, and that's 16 kilobytes to start. And then you keep on adding pages to this directory structure depending on how much real memory you're accessing in which memory zones. So you started that, you're able to minimally use the page tables that are really where your mappings are. Let us look at another example here, and we have the same sample number that we had, the one that has 4C2 as the first lowest 12 bits. We convert this to the binary number as given here, then 9 bits, we take the top 36 bits and take 9 bits out sequentially out of that and put the offsets into the PML4T table, the PDPT table, the offsets for the PDT table and the PT table. And those offsets in this calculation come up to be, the first offset is 255 into the PML4T table. That offset will have the address of the PDPT table, and that offset here is calculated to 379. So you will go to number 379 and find the entry you're looking for and then you get the next offset in the next table. So you will traverse basically these records and finally get the offset to your page frame table. And the first table, PML4T, because it's the first table, there will be only one per process of this table. But the next table, because the first one can address 512 of those, the PDPT table, you will actually have 512 possibilities of those tables. Not that you will actually use them, but there is a possibility to have 512 of those. And then the next level can have 512 times another 512. So the level, as the level goes to the right, the number of tables you can have will increase. But realistically, all you will need is based on the actual virtual memory that you need to use. And that's about the allocation you need. So 4K is there, but you're also able to use larger page sizes. And in the x86 64-bit architecture, you can go from 4K page size to the next page size of 2 megabyte. So why is it so discrete? Why can I not go 4K to 8K? Well, the reason is that what happens with the addressing structure is you had 36 bits used for page mapping and 12 bits used for the offset within the page. So the next logical choice here is you take one page table or one page directory table out of that mix and say, I'm just going to use 3 page directories to map finally into the page frame. So you take 9 bits out of 36 and you say, okay, my page table structures will only use 27 bits now. And I'll move the 9 bits into the page offset. So my page offset uses 21 bits instead of 12 bits. And with 21 bits, you're able to address 2 megabytes of page sizes. So similar structure, you can apply the same example and say, okay, what if I was using a 2 megabyte page size? How would that lookup have been? Similarly, the next level after 2 megabytes that is supported is 1 gigabyte, and the rationale there is pretty much the same as the 2 megabyte rationale, which is move another 9 bits over to the offset addressing. So you increase the offset from 21 bits to 30 bits, and then use only 18 bits for the directory tables for the page mapping. As you increase the page size, your ability to distribute memory to lower sizes reduces, but you need lesser number of pages. And that's the balance that you strike here. The default is still at 4K though in systems, but systems do offer for partial sets of data. At least in Linux, you can get huge pages and choose partial data sets where you do not want 4K page sizing because you know you need the larger page size and you want to have an efficient program that is going through less of the page table entry mappings. So how does Linux kernel support paging? Linux kernel supports the paging at both the levels that the Intel x86 supports at 4-level paging and 5-level paging. 4-level paging is used for 48 bits and 5-level paging is already available if you were to use 57 bits, which gives you even more data. But 5-level paging is not really in use, but it's already in the code. And not really in use because you don't need to actually address that much memory. Then the kernel has the responsibility to manage the page level global directory updates. Whatever data is there, what it wants to map, because the kernel owns the allocation to the memory. It also puts the process's page directory in the CR3 every time there's a context switch. Because it doesn't want, as the context switches, you don't want the previous process's data to be accessed. So the kernel is responsible to make those switches as well. The other thing that happens in context switches is that the cache entries should be removed because they belong to the previous process. So that happens explicitly and implicitly as you actually change the CR3 table entry in Intel in the processor. There are also naming differences, in the Linux kernel, you will use names like the page global directory, page upper directory, page middle directory, and page table. And on the x86 4-level paging, the names you're using were page map level 4 table, page directory pointer table, page directory table, and page table. So this is the view from the CPU perspective on mapping memory pages. This way the CPU has the ability to provide a linear address space to all the processes in a multiprocessing system that will be operating on it without trampling over each other and keeping security intact. How this is actually used and how this gets managed is through the kernel, which plays a privileged role. So in the next lecture, we will get into process memory. How does actually a process use this memory and operate?